All right. Most exciting part. So, fundamental to the idea of related rates is not letting things become constants too early. That's a fundamental idea of the whole thing, right? So be really careful about plugging stuff in too early before you take derivatives. The only things you're allowed to keep constant are things that actually stay constant, like that drone problem where it was constantly 25 meters up, the plane problem when it was constantly 1 mile above the ground or whatever, right? The lamppost problem where it's constantly 15 feet tall, the lamppost thankfully wasn't changing height. Okay. There is one thing I want to talk about that's going to come up later, that came up earlier, so I want to talk about it right now. Remind me again, what's another way to say dy dx?
Y prime.
Y prime, or even more generally, f prime of x, is that correct?
Mm-hmm.
So then if I multiply the dx up, I get this.
Differentials.
Now, I could do something like this directly. If I give us a function x cubed, I could then say dy equals 3x squared dx. Jump straight to there because dy dx would equal 3x squared, so I just throw the dx up. Later this semester this is going to come back. But do you see how this is just one step away from dy dx equals 3x squared? It's the same thing, I just multiply the dx up. Okay. All right. I just want to say that since I came up. I want to say that before I forgot.
And there's also a change in y.
Yeah, we talked about that before. I'm not overly concerned about this. So we need to finish up this worksheet from last time. Does anyone need this? See me after. You're somewhere in there. Yeah. So we stopped short here, if I remember correctly. We did this side, but we stopped short on this side, if I remember correctly.
Mm-hmm.
So I'm not going to redo all of this, but what we introduced last time was what a second derivative tells us. So the first few steps are very familiar. Take a derivative, figure out where it goes to 0, or where it's undefined. In this case, I only had places where it was 0. That tells me how to set up my sign diagram. What does this thing investigate exactly? What does that sign diagram investigate?
It determines how the basically.
True, but what's it directly investigate? True, because it's looking at what? What does the minus and the plus mean?
There's a change in sign.
Of what?
Slope.
Slope. Okay, good. So this sign diagram investigates the slope of the function, correct? Which leads to what Mercedes says: when I see a minus, that must be where it's decreasing. When I see a plus, that must be where the function's increasing. And if it decreases and then increases, that must have been a minimum it just went through. That only makes physical sense. Why is 0? 0 is a critical number, right? Why is it not a max or a min?
Slope doesn't change.
Slope doesn't change on either side. Just sort of rest there for a second, yes? Climb a mountain. Oh, okay, go on. Right? So how did we get this?
We plugged -1 back into the original function.
Original function. So whenever you want to know the point where the function is, you have to use the function. Don't plug it into the derivative because I already know it's 0 there. So be very careful. You have to be aware of what you need in the moment and what thing is going to give it to you. The function tells you where the points are. First derivative tells you slope. Second derivative tells you
The
concavity.
concavity.
I like it. Is it happy?
Sure.
Okay. Blah, 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 blah. Then we did a second derivative because we're all insane. We found critical numbers and they looked really pretty. We did a sign diagram for it, but now wherever I see pluses, that's concave up, happy. Wherever I see negatives, that's concave down, sad. You can't beat that shit. Yes? Concave down. Looks like a sad face, and it's freaking worse than negative. That makes beautiful sense. Okay. And where we left off, I didn't feel like trying to do that in my head. And I was really lazy, I didn't go get a calculator. So now let's figure out what this inflection point is. So I just have to plug -1 over square root of 2 into my function. My function. We're going to throw -1 over rad 2 into this guy.
-1.2.
Let me show you something real quick. You guys ever use this button down here?
No.
Stow. Well, stow button. So if I do 1 divided by the square root of 2, and I think I want negative that, right? For right now.
Yeah.
-1 divided by the square root of 2. This might be overkill for this problem, but it's fine. Okay, that's what that is, yes? Okay. Now watch this, you ready? I can store it in X. You guys all with me? And then I can just directly put the freaking thing in there, watch. 5x cubed minus 3x to the 5th. Go! Did you guys do that? Did you get this?
Yeah.
Anybody?
Mhm.
You're like, no, man, we knew you were going to, so. No, work smarter, not harder. Well, -1.2 roughly. Okay. And then I can plug in, so if I put a +1 over rad 2, it's just going to be the opposite side. And for this function, be really careful. Don't do that all the damn time. Okay. So be really careful. Don't just assume that. And then when I plug a 0 in, of course, I get freaking 0. What are these points again?
Inflection points?
And what is an inflection point?
When the concavity changes.
When the concavity changes. It's kind of like the joint between those two parts. You have this kind of pipe and you have this kind of pipe, and you weld those suckers together. The inflection point is where you weld them. If I had a place, like if this was plus, this would not be an inflection point, and that would not be an inflection point because the concavity would not have changed. Just like why 0 wasn't a max or a min earlier because the sign didn't change. Inflection points are where concavity changes. Does that make sense? There's a lot of analogy between first derivative stuff we do and second derivative stuff we do, yeah.
When we were making the sign diagram, do we plug those values into the derivative or the second derivative?
When we're doing this sign diagram, we're investigating concavity. And which derivative tells me concavity? No, first derivative tells me slope. Second derivative tells me concavity. So I plug stuff into this dude. Because that's the one we're investigating in that moment. Yeah. Yeah, all these critical numbers are critical numbers for F double prime. So everything here's got to be about F double prime. Okay. So let's see. We know some intercepts already. We know 1. We got 0, 0, correct?
Yes.
Do you guys, can you find any more intercepts? That's the y and an x intercept, yes?
Mhm.
Can you guys take a moment and figure out if there's any more intercepts? How do you know?
Because if that's the y and x, then you don't have it anymore.
There could be multiple x. There could be more x-intercepts.
Second derivative equal to 0?
No. I want to know the intercepts of the function, which are points on the function. So what am I going to look at? F. I'm going to look at F. F in the chat. Okay. So I want to know the intercepts for this guy. Y-intercept is easy. We already got it. It would be make x 0. How do I find the x-intercepts? Sure. So for almost every function, what's going to be involved in finding the x-intercepts?
Factoring.
Factoring, yes. So what comes out of this thing?
5x, x cubed.
X cubed, 11.
Use 5 minus x squared.
Kick ass. So there's x equals 0, right?
Mhm.
So that's the one we knew. There's two more, yes? Okay. How do I find the other two?
Set 5.
Go ahead and do it. I'll wait. So to find x-intercepts, I set the output to 0. That's why it involves factoring so often, because I normally have to factor like polynomial stuff to get where it's 0, right? So I already got x equals 0 as one idea.
Plus or minus.
Yeah, once I take the square root, yeah. Square root, square root. Alright, so then I got a square root of 5/3. Somebody help me out, what is that roughly? I'm gonna say 1.12.
1.2.
So 1.3?
Yeah.
Are you guys understanding? I'm gonna do it by hand. Go out to one decimal place to do things by hand, correct? Go ahead and try to plot some of the stuff we know already. While I go and move some. I was like, who the hell's out there? Did you know this is a college? Classes are happening? Okay. Alright, so we got intercepts. We have inflection point kind of stuff. We have maxes and mins. So what's it look like my scale should be on my x-axis, for example? I mean, kind of my biggest output, my biggest inputs are I think the 1.3, right? Yeah, so here's where you can be really nice to yourself. Double check me. I think the biggest in any point that means something to us, yeah, the biggest x's are the 1.3s. So watch what I can do. I can be really nice to myself. At the very least, I can make this negative 0.5, negative 1. I could have been even nicer, but still, I'm going to do baby steps here. Just in case you're not even aware you can do this stuff. So when you have very, very small inputs or outputs or whatever, just make your scale small. So you kind of zoom in. I don't want an answer to be something like, and I'm like, what is going on in there? Blow that thing up. Okay. And that's the sound this makes. All right. Yes?
Doesn't that get rid of the curve, like, at the ends?
What do you mean?
Like, when it curves, like, in the beginning of the function, when it curves in?
We'll see. I think I know what you're worried about, but it ain't gonna happen. Okay. So what can we plot here? We know there's a 0, 0, 1.30, negative 1.30, We've got inflection points. This was like, what was it? Oh, a negative point, so there it is. Why did I do this to myself? So negative 0.7, negative 1.2. So now I can make my Y scale. Let's look at my outputs. What are my biggest outputs? My biggest outputs look to be 2 and negative 2, yeah? Are you guys all understanding? So once you get all the calculus and algebra shit done, then you worry about your scale. And how do you determine your scale? Look at every point that you're going to need to plot and just base it on what's the biggest of each. So again, I could be kind of nice to myself. Let's go 1, 2. Let me make sure I didn't miss anybody. Yeah. And then negative 1, negative 2. Cool. So I got a minimum and negative 1, negative 2. Minimum, negative 1, negative 2. I'm going to put right underneath here, I'm going to put min. The reason I'm doing that is because I am a poor little human. I have no programming. I have to. So when I hit that point, I've given myself a little note. Hey, Jeff, turn, because this is the minimum, right? I don't want to go lower than this, so I'm going to turn. So give yourself little post-it notes. Right? Okay. They don't have to be literal post-it notes. Maximum is 1, 2. Max. Check, check. Then I got inflection points at negative 0.7, 1, negative 1.2, negative 0.7, negative 1.2. There's an inflection point, IP. And then 0, 0 is an inflection point. And then 0.7, positive 1.2 is an inflection point. Oh yeah, I remember this graph. That graph gets crazy.
Yeah.
Okay. So did I miss anything? Let's see. I've got all my inflection points. I got all my maxes and mins. I got all my everything. Okay, good. So help me out. There's one other thing we can do. Go back up here. I could have asked from the beginning what the end behavior was. Does anyone remember what the end behavior is of this?
Even, going up, down.
It's not even. Definitely not even, because both powers are odd. So
So if it's odd, it's.
yeah, it all matters on the highest power. So it's going to be like a cactus. Let me make sure from your perspective. From your perspective, it would be this, but it's negative. Yes.
Yeah.
So it's been flipped. I think that's from your perspective. So it's going to start up here. Yeah?
Mhm.
It's going to go down. So let's see. I know I start with a up concavity, and I know I'm decreasing. So everything seems to be matching up pretty nicely. So I know I'm going to decrease, and I have an up concavity. So instead of being something somebody could, it would be this that would hold water, not this that would have water fly off of it. Okay. So I'm going to come at it like, it should be curvy, but that's too bad. That's the minimum. When do I become not cup up? When
At
do
the
I
first
change?
inflection point?
Yeah, so at this inflection point, let me just stop here. See, I should have made this even better. I could have made the scale even better. I could have made it go by 0.25 maybe. Yes? Yes?
What's that IP that you're stopping at right now?
That's the inflection point.
Inflection.
Yeah. I like it. That's not me making a declarative statement. That's it. What's going to happen at the inflection point?
It's gonna
Switches. So
switch.
now what concavity does it have?
That has cut
So
down.
far it's had an up concavity. Now it's going to have a down concavity, right? That doesn't mean it's going to go down. That just means it's going to be curved down. Yes? So what I have to go up, don't I? Because what's the next thing I have to hit?
Another inflection point.
Well, the 0, 0, correct? Which happens to be another inflection point. So now it kind of curves. You can even start here and make sure that you're going to cup down. See that? So overstate your shapes. Just to really make it clear, I know what you know. Now what concavity do I have?
Up.
Concave up until I get to here. Because that's a what? So do you see how desperately important it is to label each point as you plot them? Because then as you graph, you're telling yourself, now do this, now do this, now do this. You don't have to remember it, you have to go back and check. So now I've got, and is there any more inflection points after this?
Nope.
So I'm going to be concave down the whole time. So now I can just sort of, what I like to do is start at what would be like sort of a vertex. Make it definitely cut down. Make it definitely cut down. Okay. It looks like it's going straight up and down, but that's just because it's so smooshed.
Could you just show me where the inflection points were?
Yeah, all the ones that say IP.
No, I mean like where you got them.
Oh, where they came from? Okay. Right there. So this is this.
Oh yeah.
Concavity up, concavity down, that must be an inflection point. Bam, bam, I had so many inflection points.
So as soon as it shifts in concavity, like if it goes like this or like that, that's when you know.
Yeah, whenever it shifts from concavity, that's an inflection point right there. The tip of my thumb is The tip of my thumb is an inflection point.
Yeah.
And then you can just throw it in the calculator and take a look. I highly recommend you do not graph a problem like this in a quiz or a test first. Because then you might try to make it match what it's supposed to be, and you can't do that well enough that I know you're doing that. Okay. Well, let's see real quick. If I put this in the old calculator, let's see how close we got to things. Where'd it go? 5x cubed minus 3x to the fifth. And I'm going to make the scale the same, so it kind of matches better. I'm going to go to my window. My scale goes up to 2.5 for the y, right? And down to negative 2.5. You guys kind of with me? You don't have to do this, but it's better. My y scale goes up to 2.5 also, yeah? Interesting. Oh yeah, I did exactly the same. Negative 2.5 to 2.5. You guys kind of with me? I'm just changing my y max and my y min to match what I did so that it compares easier.
Do you need to change the scale too? 'Cause
That way they look the
yours
same.
has a different
Well,
scale.
that just has how many tick marks they put. So sure, I can make my scale 0.5 for both. Sure, and now it's just gonna put a tick mark at every 0.5. That wouldn't change at all the shape of it.
It would make it look
It's just
more
how many
straight.
tick marks they used. Yeah, that was crazy fast. Damn. Yes.
Can you repeat that, what you said about in-range behavior again? Like how, because it was odd power, that's why it started at.
Yeah, any odd power is gonna look like, let me make sure it's from your perspective correct, this. Like a cubic. I call it cubish. One of my colleagues calls it a giraffe graph, because it looks like this is the head of a giraffe, and I was joking because it's missing his front leg, and that's horrible. Why is the giraffe not falling over? Anyway, sorry. I always mess this stuff up. Giraffe graph, interesting. It's gonna fall over. Negative would just make it go like that. Just flips over the x-axis, right?
We have the negative because the highest power.
Highest power is negative, yeah. So the highest power is what determines the end behavior. If that would have said 5x cubed minus 3x to the fourth, then the end behavior would have been this. It would have been a parabola, because that's what even powers look like. Reflected, yeah. All right. Now, just because I know you cannot get enough of this, somewhere, here it is. One more.
Who's gonna go on the board?
Yeah, give you one, right? Anytime. You're welcome, Brett. Okay, everybody got one? You guys got one? Yes, okay. Oh, God, I just never have enough time, okay. Does this look, you know, you guys remember pre-calculus?
Yeah.
I know some of you guys are gonna say no just to protect yourself. I don't know. I don't know where it was. That's the rational function, correct? What about the x minus 1? What does that lead to?
That if the bottom is 0, then
Domain
it's
problems, which leads to what graphically?
One is.
a
Vertical asymptote, right? It's a trap. Right, so that's where you can't cross that wall because the function would freak the shit out, so your function must kind of slam up against it, right? Good old vertical asymptotes come from the domain. What about horizontal asymptote? What situation am I in? Does anyone remember?
you're in
Slant.
or the one where the oh my god.
You got it, slants, oblique, they all mean the same thing. You're gonna have an asymptote like this.
Yeah.
Yay, Jeff. Okay. Just to kind of point out a couple things, because I am going to ask you about it down here. Domain, easy. What's domain?
Negative infinity to 1.
I love all you technical
Union.
people. X not 1. Okay. X can't be 1. You could write it as, but I mean, X not, it's not 1. I know, I'm sorry. You bad people. Sometimes you're so freaking picky. Just for the sake of time, and I'm sure you're not gonna cry. You could do this later. That's the derivative, okay? We don't have time. But how do you find the critical numbers? What's one critical number you can just see? Can anyone just see a critical number?
1.
Yes. Now, why is that actually not a critical number?
Because
It's
one
not the domain.
can't.
11. So 1 does make the derivative undefined, but it also makes the original function undefined, so it's not even a candidate to be anything. Now, at the same time, let me remind myself, we are going to still use it, because couldn't the function be going down on one side but down on the other side also? But couldn't it also be going up on the other side? Okay, so we still have to consider it as a critical number. It's just not going to be the location of a point, because it makes the function undefined. But still, I could have a changing slope on both sides, down to up. What are the other critical numbers going to come from?
Zeros over the way.
Yeah, so if I take a 2 out of the top, how do you factor this business?
-4 and +2.
Yes. So what are my other critical numbers?
4 and -2.
11. So this one's undefined, these two are zeros, yes? Us. Sign diagram, so I'm going to put down on my sign diagram, I'm going to put -2, I'm going to put 1, I'm going to put 4, over the -2 I'm going to put a z, I'm going to put a u, and I'm going to put a z. So now I'm investigating the first derivative, I'm trying to see where it's increasing, decreasing, so where am I going to plug stuff into? F prime, yeah. How we doing? What's the multiplicity? I'm going to keep pushing this.
1
The multiplicity on -2.
is 1.
1. Multiplicity on 4.
1.
Multiplicity on 1. Ah, so this is even, odd, odd. Multiplicity, yes? What the hell does that mean, Jeff? Well, I have a beautiful shortcut, remember? I don't have to investigate every damn region. Because I'm clever. If I put a 5 in, what kind of a number do I get out? It's easier to look at this, to be honest. Let me put this fully factored form here. So I get 5. I put positive times positive over positive. Yes. Positive. Okay, good. What's it going to do around 4? Change sign. What's it going to do around 1? Stay the same sign. It's going to bounce off. It's going to look like a parabola there. And what's it going to do around -2? Change sign. If you don't like the multiplicity, if you don't think you're going to remember it, you could just plug numbers in from every region. That's fine. So, what's true about -2? What is that the location of?
Local maximum.
Yes, because it goes up and then comes down. What's true about 1? Anything?
No. Well,
No.
it's undefined, but
Yeah, it's undefined, poor little dude. But he's not like a Max Herman. What about 4?
that's a local
Minimum, because it goes down and it goes up. All right, let me stop for a minute, right? All this is the same thing we did for the other 2 problems. The only difference on this problem is I've got other things to identify from the function itself. Asymptotes, domain, problem solve, this kind of stuff. Where am I going to put this? I'll tell you where to put that. Be quiet.
in the original function.
Original function. So let's see, we get 8 minus 32 is -24 over -3 is 8. Please double check me. The negatives cancel. I'm pretty sure that's 8. Is that what I just said? Shit. Yes. Y'all can just trust me, or you can double check. -24 over, yeah, that's 8. And then 4 would be 32 plus 64 is 96 divided by 3 is 32?
Yeah.
Thank you, man. Feels like it should be negative or something. Where did I put that? Here? Yes. Feels very, oh, that's right, because we have this weird thing here. Okay, that'll be fun. Do you guys see what I was worried about for a second before I remembered that there's a weird place? Do you guys see how the minimum is higher than the maximum? But it's fine. We'll see. For example, real quick, has anyone ever seen a graph that looks like this? So there could be a minimum here and a maximum here, for example, right? So that could be what's going on. We're gonna find out.
Very different neighborhoods.
Yeah, they're in totally different little neighborhoods, exactly. So this whole neighborhood's up here and this other neighborhood's down there. Yeah. Small, big fish, small pond. Huh?
Big town, small town.
Big town, small town. I'm not too, God, can you guys see the intervals where this thing is increasing?
Yeah.
Yeah, -infinity, -2. Okay, we're not gonna write that down. How would you write where it's decreasing though? Could you do one interval? -2 to 4? No, because at 1 it's undefined, so you have to have 2 intervals for decrease.
So it's like -2 to 1.
-2 to 1, 1 to 4, I love it, okay. Yay, we got the second derivative, okay. What's the only critical number for the second derivative?
1.
And again, it's not a valid input for the function, but I still have to consider it because it's where the concavity could change on either side of it, yeah.
I was wondering, it might be off topic, but would we ever have an example where it's like there's 2 different critical numbers?
Of course, yeah. We had 3 up here. Yeah, there's 3 critical numbers. Yeah. Okay. Here we just had 1, which is awesome. So sign diagram, 1. Undefined. So if I plug in 0, what's the sign on this? Negative.
Negative.
And if I plug in a 2, the sign is positive. So that means it's concave
Down.
down.
And concave.
Up. Okay. So what's true about 1 then?
That it has to be an inflection point.
Yeah, which is weird. It's not really a point. Because if I try to plug 1 in, I get nothing out. But it is officially kind of like where concavity changes. I really want to make sure you understand this. The concavity, and a really easy example of this is here. I already drew it. What's the concavity here?
Down.
And what's the concavity here?
Up.
Up. But there's no inflection point because it happened around some weird ass asymptote, yes? That's exactly what's going to happen here. Okay. Oh, come back here. Intercepts, really quickly. What are the x-intercepts? Who the what? Take the 2x out, you get x plus 8, right? So you get 0 and negative 8, is that okay? What about the y-intercept? It's already there, yes? Okay, I like it, I like it. So we got our x-intercepts, we got our y-intercepts. What about asymptotes? Vertical asymptote.
At 1.
1. Horizontal asymptote. Slant. And you remember how to find a slant asymptote? Nope, that's the horizontal asymptote.
Long division.
Long division or just division. What kind of division can I use here? Synthetic. Does anyone remember synthetic?
A little bit, yeah.
Sort of, but I don't.
So just a reminder, here's the problem. You guys see how there's no number here? So I'm going to put a plus 0. This is where you put a little 1 in a penalty box. And you put the coefficients. 2 comes down, times 1 is 2, add, multiply, add. If that doesn't sound familiar, find a pre-calc teacher, slap them in the face. Or slap yourself in the face if you just forgot. Otherwise, you could do long division. Does this look better?
No.
So x times what is 2x squared? 2x times x is x, 2x squared. 2x times negative 1 is negative 2x. And then what do you always do when you long divide? Subtract. So change the signs. Die, 18x. 16 to 18. 16 to 18. Synthetic, more efficient. Bring down the 0. 18x minus 18, change the signs, I get 18, so I get a remainder of 18 over x minus 1. If you have forgotten how to long divide and synthetically divide, I highly recommend you review that. If you're not sure how to review it, just reach out to me. Yes? This year? So one of the worst things about long division is to remember to change the sign each time, yes? So what we decided to do, number 1 is, the variables don't matter worth shit. Do you see how this didn't matter? Do you see how only this matters? This is what matters right there, yes? Because it leads to this. So the variables don't really matter, so I got rid of the variables. Instead of changing the sign each damn time, I'm just gonna change it once. So that's why I put a positive 1 here for x minus 1. So how do you figure out what goes here? Well, what makes him 0? Yes. Okay. And so this is 2x plus 18 over x minus 1. Now, real quick, horizontal asymptotes. I know this is slant, but let me just say. Horizontal asymptotes, slant asymptotes, they all care about what happens when x gets big. When x gets really, really big, what is 18 divided by x minus 1? Getting close to. 18 divided by a billion minus 1. 18 divided by a trillion minus 1. That's getting stupid small, so it's going to 0. So when x gets really, really big, I've got to approach that line. That's going to be my slant asymptote. Okay. So, let's see. What do we need? We need my intercepts. Where'd they go? Here they are. 0, 0, -8. So I got a -8 input, right? I've got -2 and 4 up here. So I might as well go by 2s. Yeah? 2, 4, 6, 8, 10. And then my y, I've got to get up to like 32. I think that's my most extreme y that we know of. Yes. So I might as well go by, what do you guys think? What should I go by?
8.
8? Okay. 8, 16, 24, 32. Yay! -8, -16, -20. Okay. So now I can start plotting some stuff. What's my vertical asymptote? X equals 1. So I'm going to put a wall there. Make whatever sound effect you want. So that's the shield that we're going to slam up against. I got my intercepts 0, 0, and -8, 0. I've got my max and min. -2, 8 is a max. And where'd it go? There it is. 432 is a min. What are you doing over there for? And I got a slant asymptote of 2x plus 18. So I need to put a dotted line at 2x plus 18. Tell me anything about 2x plus 18.
That it's a slant.
Y-intercept is 18. There we go. And instead of trying to do slope, because see how my scale is freaky as shit? Let's just plug a number in. Like if I plug a 10 in, what do I get?
24 or 28.
38. 32, this would be, what did it do? By 8? 40. So 38 would be about right there. So then my slant asymptote goes like, wait, am I going through the right place? No, Jeff. Damn it. I love it. Gotta keep track. Oh yeah, this is where I want to go. Damn it. That sucks a lot. Oh boy, that's really bad. That's really, really bad. Oh man. I was about to try to find a straight edge and I should have. This, yeah. This has had some trouble. But real quick, I can salvage this maybe. Do you see up here? Do you see up here how this goes like this? When you put your walls in, your function's got to live within them, yes? Do you see how that makes sense to be a minimum? Okay. And then this is a maximum here because it's got to kind of go like this, yes? So this has got to go up against this wall. You see that? Now I should be really careful. I should be a little more careful. For a second I was back in pre-calculus. Okay. This concavity is up forever after 1, correct? So do you see how I accidentally did that right? Concavity is up, yes? Concavity is down everywhere below 1. So do you see how that kind of fills in over here? That's supposed to be a maximum? Brandon, what's up?
How is the square right there, the 16, it's right above the 16, is that slant asymptote?
This here is a slant asymptote, yes. It had a little rough time getting born. Poor little dude.
So that's 18?
Yeah, it's supposed to be going through 18, yes.
Gotcha.
16 to 24, so 18 is roughly right there.
Yeah. Okay.
So this is supposed to be, you guys see how this has got to approach that asymptote, yes? Then it's got to turn, see how it's concave down all the way through? Then it's got to go through that point, and then it's got to approach that. So it's concave down forever on that side. And again, to check this, you could just graph it in your calculator. Okay. Let's take a 10-minute break, come back 20 after, and then we're gonna do 4-2 and somehow 4-4. For what now?
For our second derivative, what were the critical numbers?
Anyway, like that.
Because if you're measuring on a graph or something. That's just confusing.
Just one on this one. I mean, this one.
Yeah.
Yeah, because that's the only. If nothing makes it
It's like
zero,
I was going on a graph,
but one makes it
like way
undefined.
up here, and I use the slope to work like except just like has to make sense for me to actually be able to do it, because otherwise I get.
Now, somebody asked me about the fact that the way I drew this, it goes through the slant asymptote.
You gotta get through those.
Part of that, I think, is just because I don't know if you guys noticed, I did a horrible job of drawing in the slant asymptote. Just in case you didn't notice. So it actually shouldn't go through the slant asymptote, but can it go through the slant asymptote? Of course. How many times could it go through the slant asymptote? An infinite number of times. Because all these slant asymptote or horizontal, all they say is, get closer to me over time. So I could have a cosine going it hits the horizontal asymptote a million times, infinite number of times. But it's getting closer and closer and closer as I go out, as long as the amplitude is getting smaller and smaller. Does that make sense? I just have to get closer to the horizontal asymptote. Vertical asymptotes say, you cannot exist here. If you try to come here, things freak this shit out, right? Horizontal asymptotes say, you eventually got to get close to me. So normally you see it do this kind of thing, the asymptotic high five, right? But it could do this. It's still getting closer over time. It just is getting closer from both sides. Okay. Now, 4.2, we skipped it for a moment.
That should right technically I just did fractions.
4.2 has two theorems in it, and they both are basically the same thing, which is kind of fun. The reason we let both stand is one is the more general one, and the other one a dude found out about on his own. So we gave the guy some credit, and according to the history of math, it could have been, he could have stole it from somebody, who knows? So. So there's a theorem called Rolle's theorem. Yeah, that's fine. I was thinking about starting with the other dude and working back, but we'll start with this guy. What this guy said was, if I have a function that is continuous and differentiable on AB. So on this certain interval, it's continuous and differentiable. So it has no teleportation, it's got no kink in it. You guys come with me. It's got to behave well. It can't suddenly teleport, it can't suddenly jump, it can't have a discontinuity. And f of A equals f of B. So before we go to the then, let's figure out what this looks like. So this could look very simple. So let me just say, here's A, here's B, yes? So all I need is that the output at A is the same as the output at B. So whatever that is, it's got to be the same here, yes? Now, how could I connect those 2 points? What's the simplest way I could connect them? Straight across. Are there any other ways to connect them? Yes. So one way to connect them is straight across. We'll call this one as the crow flies. Is that cool? You guys ever heard that phrase? As the crow flies? You know, like, no man, we're not ancient like you are, shut up. Now, another way I could connect them would be maybe like this, yes? If I start going up, in order, this is going to be really silly. Because I'm continuous and differentiable, what's the only way I could possibly connect back over where I'm supposed to connect? is if I freaking come down. Now, if I come down, somewhere in the middle, I'm going to have a point where the slope is parallel to the crow flies way, yes? That's actually all Rolle's theorem says. If I have a function that is continuous and differentiable, so it's not allowed to jump and teleport and do weird shit, and its output here is the same as its output there, it has to have at least one place where the slope is equal to straight across, is equal to, in this case, 0. So the therefore is, or the then is, there exists, that's the there exists. Let me not do that to you, I'm sorry. There exists a C in AB where f prime of C equals 0. So that's the technical speak for there's a freaking place where it's got a horizontal tangent line. The minute it goes up from A, at some point it's got to come back down, so it's got to have a freaking place where it's got a flat slope. Does that just make sense? What if I went down from A, Jeff? Well, then you got to come back up. What if I did many? Then you have more than one place, yes? So there's got to be at least one point where the slope of that point is 0, where the tangent line is horizontal. Does that make physical sense? The minute I go away, I eventually have to come back, which means in the middle, I've got to have a flat place. Was the only way I couldn't if I was allowed to teleport and put a kink in there. But I'm not allowed to do any of that shit.
So with concepts like this, we never have like asymptotes or.
Oh, the function we're looking at can't be freaky between the A and the B that we're given. That's a nice way to say it. So, yeah, we can't have asymptotes over. I like it. So I love that. If I'm a student here, I'm like, all right, so it's got to be a nice function. Okay, good. I can live with that shit, especially after what we just did. You're gotcha. Yeah. You lost. You made some enemies. Okay, well, I'm a math teacher. Me too. So, how do we feel about Rolle's theorem? How the shit do you apply it would be a great question. You're all like, okay, what do I do with that? What is the homework going to look like? Always a really good question if I were you. So let me see. Let me pick out a homework problem. Let me use my glasses because I'm thinking all the shit. Okay. Blah blah blah. There we go. Okay, perfect. All right. Pretty sure I didn't assign this one, so I'm going to do it.
You sure about that though?
I don't care. Do you really want me to check, Brandon?
No.
There you go. That's the smart thing, is just let him do it. Let him do it. So first off, how do I verify that the requirements are met? How many requirements were there? You guys remember?
2.
3.
Oh.
There we go. With it. The 2 you're thinking of are continuous, differentiable. Do you agree with me that that's a polynomial? All polynomials are continuous and differential. They're the real MPP. What's the third condition for Rolle's theorem? That's the results. FA equals FB. So more specifically, what has to be true? F of -2 must equal F of 2. So if you plug -2 in, what do you get? -8 minus 8? Is that right? -8 minus 8 is -16. Plus 8 is -8 plus 2 is -6. If you plug 2 in, you get 8 minus 8. 0 minus 8 plus 2 is -6. Okay, so you get -6 either way. You guys kind of with me? Okay, you guys have a calculator. You can plug -2 into it, but you understand what I just did. I have to make sure that f of a equals f of b. That's guaranteed. That what's the slope if I went straight between the points? 0. Therefore, whatever my function does, it's a freaking polynomial, so we know it's a little Loch Ness monster. It's got to have at least one point where it's got a flat tangent line. So how do I start to investigate that?
Take the derivative and set it equal to 0.
Yeah. F prime, 3x squared minus 4x minus 4. Set that equal to 0. Let me see if you guys are cool with this. Do you see how this got to be a 3x and this got to be an x? Do you see this is negative 12? What factions in negative 12 add to be negative 4, negative 6, and 2? If I make this a 2 and this is a negative 2, this is negative 6 and this is 2. Alright, so the more you can play with numbers, the easier that shit is. Or you can do surefire method, whatever the hell, right? Alright, so where is this equal to 0? At 2, negative 2/3. So does this work? No, because it's not inside. It's at the end point. Did I find a point inside? Is negative 2/3 in this interval? Yes.
Wait, why can't it?
This is at the end point. It's got to be inside the interval. Yeah. Okay. That's Rolle's theorem. And it's just like finding horizontal tangent lines. You just have to verify the 3 things are true before you continue. Now, here's what's funny. I can't do this with this. Yeah. Rolle's theorem, yes? In fact, let me do this even better. Get out. Okay. Get out.
Oh my gosh.
Rolle's theorem. Rolle's theorem, yes? Yes. And then it's got to be at least one place that's got a flat. Is that cool? Okay, you ready? This is what I couldn't do with my stupid little iPad. Old technology better. You ready? Sorry. So now I don't have to have a 0 slope. F of A does not have to equal F of E. But do you see how, if I have F now, let me give us some, there. There's my XY, yes?
Sure.
Sure, Jack, whatever the shit. I don't know what you're doing, man. Well, neither do I. Does F of A equal F of B?
Yes.
Does F of A
Wait,
equal F
no.
of B?
No.
But I can still, I need you to really get this. Here's Rolle's theorem. If I had my lines here, it's got to have a slope that's similar, that's equal to this. If I rotate it, the same idea applies. Whatever this slope is, it's not 0, is it? Can somebody tell me what this slope is? This is where you guys look at me like I'm crazy, but what is that slope? You can do it. What's the slope? How do you figure out the slope? Y2? What's Y2? I'll get it started. Keep going.
F of A. All over A minus B, or B minus A.
In this situation, you agree this is not 0?
Yeah.
Now, dear God, if it makes sense, if it is 0, there's got to be somewhere that's got the same slope. Doing this, it's still the same stupid idea, except now there's got to be at least one place that has the same slope. It just won't be 0. That's the more general theorem. Rolle's theorem is a special case. What if these are equal? Then it's a 0 slope I'm looking for, yes? If they're not equal, then it's whatever the hell other slope it is. Okay, maybe. They're the same theorem, just one is rotated from the other one. They're the same theorem. But we wanted to give Rolle some, we're like, good job, Rolle, you got it. Well, we got a more general thing, but still, we'll give you a name. Yes?
What was the, so there's 3 things that you have to have for Rolle's theorem to be true. What's the?
Continuous, differentiable, F of A equals F of B.
Yeah,
What about
and
for
then
mean value
what's
theorem?
What's the?
I'm sorry, that's the name of this, by the way. The name of the more general theorem is mean value theorem. Right? We're just being very upfront about the fact that we're mean. Mean, and I value being mean a lot. Theorem.
So then what's
Heretofore known as the MVT.
What's like the then?
There's only 2 conditions for mean value theorem, because does F of A have to equal F of B? No. So all I need is continuous differentiable function on A to B. Then I'm guaranteed. So here's what mean value theorem says. Mean value theorem says F is continuous and differentiable on AB. Then there exists at least one C where f prime of c equals f of b minus f of a over b minus a. Now, if I let f of b equal f of a, this is just the frickin' Rolle's theorem. What does f prime give you? Tell me an algebra name. Slope. And what does this give you? Slope. It says slope equals slope. That's all it says. So if f is continuous and differentiable from a to b, the crow fly sets up a slope, and whatever my function does to connect them, there must be at least one place that has that same slope. That's all that says. Either I connect them straight, in which case every freaking point has the same slope. You guys with me? If I had f of a, and f of b, and I connect them with a straight line, the whole damn thing has the same slope. It's just a straight line. The minute I go away, I have to have a place where I come back, and then I'm guaranteed I have a parallel slope. I need that to make nothing but sense. There's really almost nothing to this theorem. If I go away, I gotta come back, which means somewhere in the middle, I'm parallel. Yes?
So basically, isn't this like a new part of it where it's like when it comes up, it has to come down, just makes it to where it can be diagonal?
Yes. What I'm comparing to now is to be diagonal. Yes. That's all. And that's why I did the rotation thing, because that's all Rolle's theorem, mean value theorem.
Is that the only freaky theorem?
What's that?
Is that the only like thing weird about this theorem? Where
No.
it can be diagonal?
You'll find some more things out in the homework. Yes.
You're not finding the tangent line though.
No, we're just finding where the slope is the same as the crow flies. Yeah.
Plug in your formula, set it equal to the slope that you
Yes.
found, and work it out.
Yes.
Solve
So,
variances.
really quick example. What time is it? Oh my god. Okay. Blump, 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 blump. Here we go. Alright. So far, it's been awesome. Let me do this one instead. Sure. Get out of here. You're too easy. Go away. You did a great job, but just go home. Alright, so what are the conditions?
I mean,
Function has to suck. Function's gotta be continuous where? Is this continuous everywhere? It doesn't have to be.
It has to be
1 to 4. Good. And natural log of x, 1 to 4. Beautiful, right? Is it differentiable from 1 to 4? Yeah, its derivative is what? And that works for 1 to 4. So it's differentiable at all those points, correct? It doesn't freak out at any of those points. So it's continuous, differentiable. That's all I have to show. How the shit do I do this work, Jeff? Dear God, Jeff. I have to figure out the slope 2 ways. That's all. Got to figure out the slope 2 ways. Which way do you want to do it first? You got a calculus way, and then you got an algebra way.
Calculus.
Calculus is crazy. I love you guys. Look at you. First day you would have said that shit. Now you're like, let's do some calculus, man. What's the derivative of natural language? That's what the shit. Okay. Got the slope that way. What's the slope the algebra way? Good. F of 4 minus f of 1 over, get out of there, 11. What are you doing? You never used it. Go. Over 4 minus 1. F of 4 is natural log of 4, right? How do you feel so far? Minus f of 1, what's f of 1? 0. Over 3. So I get natural log of 4 over 3. So what's got to be true?
That,
F prime of x must equal, what do we, the slope at some point, in fact, let's make it even more in your face. The slope at some point, C, must equal
that.
ln 4 over 3. And what is the slope at C? Don't overthink it. Don't overthink it. What's the slope at C?
is
Natural
the
log of
natural
four.
log of
1 over
4
c,
over
no.
3.
F is natural log. What's F prime? F prime is 1 over x. So what's F prime of c? 1 over c equals natural log of 4 over 3. And now you solve for c. How do you solve for c, everybody?
Multiply.
Cross multiply. So you get 3 equals c natural log of 4, divide by natural log of 4, divide by natural log of 4. C equals 3 over natural log of 4. Can somebody tell me what that is roughly? Can you do it, Jeff? No. I'm gonna say 1.9.
2.1.
Damn it! I went the wrong way. I was at 2 and I was like, I think I go that way. Alright. Damn it. No, Jeff, it wasn't that. It was 2.1?
2.16.
Kick ass. Is that in the interval that was acceptable?
Yes.
It's acceptable! Cool.
Do you put a check mark next to it, or?
Sure, check. Yes.
What if it was not accepted?
Well, then something went wrong. If the conditions are met, there must be at least one place in the interval where it's true. So if the only answer you got was 6, you did something wrong. Either you thought it was good and it wasn't, like it didn't meet one of the requirements, or you did your derivative wrong, or you did your stuff down here wrong. Yeah, okay. You're guaranteed at least one place will work in the interval if it's continuous and differential. I love you guys. Because the idea is really silly, simple. If I start to turn away, I gotta turn back. There's gotta be somewhere that's parallel. Because I'm not allowed to just teleport myself somewhere. So I can't help but be parallel somewhere. Okay, maybe. So, last thing for today. Dear God, Jeff. You let us out so early every time. Too bad. 4.4. Here's where some of you are finally going to be able to use something you've somehow been using already. Which, bless you. No, hopefully you can use it derivatives. Yeah, now's the time. Bring it up. Bring on your derivative. French dude.
Oh, no,
So-
L'Hopital's.
Tell me this.
Stupid thing that makes everything so much easier.
Alright, considering how little time, I'm not gonna give a deep proof of this. And you're all like, man, I'm gonna cry. We're gonna do a very surface level proof. When is this indeterminate? Can somebody give me a form that this would tell me that this is indeterminate?
0 of 0.
0 over 0. So you have to have f and g both be 0. If f wasn't 0 in your case, it wouldn't be indeterminate.
And then
It would be some kind of infinity.
isn't there
So
one
0
like
over 0
infinity
or-
times 0?
Yeah, we're gonna get there. Infinity over infinity. So one thing I wanna really make crystal clear right now. The process in 4.4, the process we're gonna use, only works for ratios. If the form you've got is indeterminate, but it's not a ratio, old French dude can't do anything for us, right? So Pythagoras is old Greek dude. This guy's name, look at him. You can call him the hospital dude. And he rolls over in his grave. Or his ashes shift, I don't know if he was creepy. Alright. So it's not the hospital, dear God. Not a sandwich. Alright. Let's just go with, I'm only gonna prove, and I'm only gonna prove it. I'm only gonna talk about the easiest case. If this is 0 over 0. This is almost too good to believe. Any function I could apply the techniques in 310 to. Dear God, we're not gonna do it. I'm gonna do it to talk about the results of this. You're not gonna suddenly have to do all of 310. You guys are looking at me like, I don't know what 310 was. What was 310? 310 was linearization.
Yes.
If I have a continuous differentiable function, can I not find a linearization? I can find a tangent line, correct? Okay. I can do that for any continuous differentiable function, yes? Okay. So whatever the shit these are, they could be the funkiest functions as long as it's continuous and differentiable. Do you all understand that they would all boil down to something like that? Now why is the y-intercept 0? Because what's it going to? 0. Okay. I need you to understand this. I can make a tangent line for both of them at A. What does A make the functions do? Go to 0. So the y-intercept is 0. I could find the slope, blah, 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 and I could get, does it matter what the slope is, right? No. What is M then? What is M? Not the number, just what is it?
Slope of that.
Slope of what? F. So what is it in symbols?
F of X.
Prime. And what's N?
Prime of X.
G prime.
G prime. What do the X's do?
Cancel out.
So what's this limit?
It's
What's the
F
limit?
F prime
No,
of
no,
X.
yeah, it's M over N, which is F prime of X over G prime of X, yes. Well, it should be A and A, but okay. So let me capture what just happened. And I kind of got us ready for this a little bit. The limit of a ratio of functions that is in an indeterminate form, including this form, even though we're not going to do the proof of that one. The proof for the infinity over infinity is just to reciprocate F and G, because if F goes to infinity, 1 over F goes to 0. Does that make sense? If F goes to infinity, 1 over F goes to 0, correct? So if I prove the 0 case, I automatically prove the infinity case, because I can just flip them. You're like, whatever, math guy. Okay. So what we just figured out is as long as I have indeterminate form and a ratio, this equals, using L'Hopital's, the limit as x goes to a, the ratio of the derivatives. Now if you think about it, if you go back in time, a lot of the limits we did in chapter 2 would be easy as shit. Some of you guys need to realize, ain't no way we could have known this because we had to learn limits before we can learn derivatives, which is what we need to know to do this. So you couldn't do that shit back in chapter 2. Some of you who did it. Now, I also can't blame you if a tutor helps you. Tutors know it. They forgot where you learned it. So when they're helping you, they might say to do it because they know it works, right? It's not your fault that they told you to do it, but they should know better. So let's do a real quick example and then get the hell out of here. Let's do 2 examples. So for all of you people that really hate factoring anything, including cubes, even especially, what form is this in? No. The limit, what form is it?
0 over 0.
0 over 0, yes? What am I allowed to use then?
L'Hopital's.
L'Hopital's. Look at that, saying it right and everything, I love it. So I normally do this for myself and for the person who's grading your shit. Tell that person and yourself when L'Hopital's is happening. What's the derivative of the top?
3x squared.
What's the derivative of the bottom?
2x.
2x.
Do you notice we did not do quotient rule? That's insane. The whole idea is the derivative of the top divided by the derivative of the bottom. Please, dear God, don't do quotient rule. Holy Jesus. Okay. What happens here?
Don't you plug in 3?
Yeah, you could. I'm gonna kill an X, so I got less shit to do. Plug a 3 in, what do you get on top?
9.
9, what do you get on the bottom? 2. Now, if you did all the work, I'm not gonna. Okay. You guys go. Yes.
So what does this limit mean?
What do you mean? Sorry.
Like, what are we doing?
So, for example, you guys remember this? We never really
Yes.
proved it. We sort of did a table. And it sort of said, ooh, it looks like it's going to 1. We never really proved it. But now, can I use L'Hopital's? What form is this in?
0 over 0.
0 over 0. So let's use L'Hopital's. L'Hopital's is like, shut up. What's the derivative of the top?
Cosine.
Cosine. Derivative of the bottom?
1.
Holy shit, what's cosine of 0?
1.
1! So now, that stupid thing, which we still didn't know, we built it off of a guess, if you remember. We just made a table and went, looks like it's going 1. Now we finally proved the damn thing. So yes, if I can do factors, it's like this is not a big deal. But if I have functions that don't factor even, now I've got a way to attack it. Now, one thing you do have to be careful about, and you're all like, you said you're gonna do two things, Joe, I know. If I take the derivative once, I can't keep taking the derivative. What's the only time L'Hopital's rule says that the ratio of the derivatives will be the same as the limit of the original is if it's in indeterminate form. If I take one derivative, I gotta step back and go, is it still indeterminate? If it isn't, get the answer. If it is, attack it with L'Hopital's rule. If you use L'Hopital's rule on something that's not indeterminate, it can make the answer different. Because then L'Hopital's like, I don't know what's gonna happen, dude, good luck. It only guaranteed to work if I have an indeterminate form. 0 over 0, infinity over infinity. And considering that, well, hey, look at that, we get time. These guys were all packing up, I thought I had less time.
But it doesn't work unless
It's a ratio.
it's a ratio.
So what was somebody about to tell me? There was another indeterminate form we knew from before.
Infinity times 0.
Infinity over infinity.
Sure, but we already talked about infinity over infinity, it's a ratio.
0 over infinity. Or is
0 over infinity is not indeterminate, that's 0.
Oh, the other way around.
It's
That's infinity.
Isn't it
So
0?
indeterminate means I can't determine the answer. Is everybody cool with the fact that that's infinity?
Yes.
Big over small is really big? Yeah, okay. So, one thing I think that came up was 1 to the infinity. I can't remember that came up.
Isn't there like 0 to something?
Yep, 0 to the 0, for example. Is that indeterminate? Yes.
That's 0.
Hell no.
That's 1 or something.
What's 0 to any power?
0.
And what's anything to 0 power? 1. So 0 to the 0 is both 0 and 1. I'm going to call that thing indeterminate. Okay. A more obvious thing is, what about this? Whoa. Or maybe less obvious. That is not 0 necessarily. It all depends on which thing is growing faster. If this is growing faster, that could come out to be negative infinity. If this is growing faster, it's infinity. If they're both growing at the same pace, it could come out to be any finite number. If they're both growing at the same rate, where do I see how fast they're growing? Now, real quick, does everybody understand that idea? It depends on which one is going to infinity faster. That is an immediate conceptual validation of L'Hopital's rule, because isn't his rule all about which thing is going to infinity faster? It's all about the rates at which they're traveling, yes? That's why L'Hopital's rule works fundamentally, because it's all about who's getting there faster. Yes?
Wouldn't infinity minus infinity be indeterminate?
That's what I just had down. Even though I've circled a lot. This is infinity minus infinity. So an example of that would be the limit as x goes to 1. Oh geez, can you make an example, Jeff? Maybe. I don't know, x squared minus 1 over x plus 2 minus x minus x squared over x plus 3. I like it. Does everybody agree with me those both go to infinity separately?
Mm-hmm.
Yeah. How could I make it become a single ratio so I can maybe attack it with L'Hopital? How do I make those two fractions become 1? Two fractions become common denominator. Yeah. So you need, if you see it in some kind of indeterminate form, you need to figure out how to put it as a single ratio, and then you're going to attack it with L'Hopital's. Real quick, here's a more straightforward one. And you're all like, man, you lied like crazy. I think somebody said this one earlier, 0 times infinity. So for example, the limit as x goes to 0 of x times natural log of x. Do you all agree that 0 in this case times negative infinity, the same idea? You guys with me?
Mm-hmm.
X goes to 0, x goes to 0. That's great. Natural log of x goes to negative infinity. Can I attack it with L'Hopital's rule?
Yes.
No.
Oh.
Why not?
Because
It's
you
not
have to
a
get-
ratio. How do I make it into a ratio? I do something really weird. I make the x go down and make it become 1 over x. Is that a ratio now?
Yeah.
So I attack it with L'Hopital's rule. I can rewrite that as natural log of x over x to the negative 1, if I want to, right?
Mhm.
So now L'Hopital's rule will work, right? So we attack it, yeah, okay. So that's the idea. If it's indeterminate, I should be able to make it a ratio somehow, and then L'Hopital's rule can be used.
So how many indeterminate forms are there?
6 that we talked about, I think.
1, 2, 3.
1 to the infinity, infinity
I
minus
got
infinity. is
7.
0. Oh yeah, so at least 6,
I
yeah.
got 7.
Okay.
I don't know if that's right.
They list them all in this
I've
section.
got
4.
0 over 0, infinity over infinity, 1 to infinity, 0 to 0,
Yes.
0 times infinity, infinity minus infinity, and 0 times negative infinity.
Oh, 0 times infinity is the same thing as 0 times negative infinity. Negative
And then
doesn't change.
what's the like the final like thing for Rolle's theorem? Like you get
There exists at least one C where f prime is equals 0. That's for Rolle's.
You just kind of gave this a tug.
I did. I trust them. And I like it. Thank you. That's all right. Yes. Thank you.
Isn't 0 times infinity